Hi guys, welcome back to the channel. In this video we are going to see the SR latch using the NOR gate. So everything including timing diagram analysis, circuit diagram and everything we are going to cover in this video. So let's get started. So in the previous video we have discussed that latches is a memory element. So if latch is a memory element, so latch itself is made up of the logic gates. So logic gates is not the memory elements. They cannot store any memory element. Then how we can build with the help of the logic gates, the latches. So let's understand how to build the latches with the help of the logic gates. Basically, if you cascade to NOT gates, again you are going to get the same output. So the output again I am cascaded, means I am attaching with the back the next the NOT gate. If you consider, I have two switches. The first one is connected with the input switch and second one is from the feedback. So when starting phase we are going to connect the circuit with the input switch, so that it will pass. Suppose the input is 0, then it will be again having the feedback as 0. So if we want the feedback to be joined with the circuit, again you are going to connect back like this. You have to connect back and again you are going to give the feedback as 0 to this. But in this major problem is, so if at a time we are giving switch and at a time we are going to connect the feedback to the circuit, so as this is very hard and at normal hardware this is not possible, because switching at a time between input and the feedback, it is very hard. So that we are going to use somewhat two input switch, means two inputted circuit. So that with the help of NOR gate we can implement that. So basically if you use the NOR gate, we can able to implement the memory element like this. So you can see over there the first input is S, the second input I took as R. So here S means set, R means reset, simply we can say. So here the final output is again cascaded with the back one. So that is known as feedback. So this is not often in every textbooks this circuit diagram is not shown. So we have another circuit diagram representation. So this and that is same, but we will represent in that format only for simply representation. So this is the thing that I am saying about. So basically this small circuit is known as latch. So we can pass the S and R and vice versa. We can pass R and S at a time. But remember one thing, S means set, R means reset. So if S dominates, the output would be Q would be 1, and R, if R dominates, means R is 1, S is 0, then output would be 0, because the R is equals to 1. And see clearly these two circuit diagrams are not same. So that is why I have represented in between OR. So I am also, while studying, I also very much confused about these two circuit diagrams, because if you pass S above, you are going to get output as Q bar the top, the first one. Or if you pass the reverse way, if you pass R for above and S as down, you are going to get Q as top output. So this is very important. So often we are going to use the second diagram in this video, because this is very simple representation, and in every perspective, in every textbooks, the second diagram is only very famous. So in this video also we are going to follow up with the second diagram, that is R, S. We are going to get output as Q bar. So before seeing the truth table of the latch and put the values inside and verify the truth table, before that we need to understand the NOR gate truth table. So if you understand the NOR gate truth table, I hope you know the NOR gate truth table, because this is the implementation of latch with the help of NOR gates. So we have another implementation with the help of the NAND gates also, because these are universal gates. So with the help of NAND gates we will see in the next video, but this video we will see just with the NOR gates. If you see the truth table of the NOR gate, if at least one input is 1, then the whole output would be 1. This is very important point in this truth table. So remember this very carefully. If at least one means one input is 1, the whole output would be 0. So this is the SR latch truth table. I hope you understood the truth table of the NOR gate. So that is the very basic thing, because that is the universal gate that we should know the truth table. So if you consider that SR latch truth table, for 0 0 that is hold, for 0 1 that is 0, that is there, for 1 0 that is 1, for 1 1 state that is forbidden. So we are going to put all the values here and we are going to cross check our values, that is Q, the next state is correct or not. So before seeing 0 0, let's start with the 0 1, because that is easy. So if you consider that reset is 1 here, because reset is dominating and set is 0, because set is not 0 means not dominating, here reset is dominating. So output would be resetted. So what is meant by reset? Reset means 0, whole output would be 0. So if you consider R is equals to 1, I am passing, S is equals to 0, I am passing. You can see in the circuit diagram as well. If R is equals to 1, or any one of the input is 1, the whole output would be 1. Now only we already saw in the NOR gate implementation or NOR gate truth table. If any one of the input is 1, the whole output would be 1. Or we can simply say, without the help of the truth table of the SR latch also, we can simply find the output of the Q is equals to 0, because if R is equals to 1, means any of the input is 1 for the NOR gate, the whole output would be 1, means the Q is equals to 0. If Q is equals to 0, Q bar is 1, we can simply say. So if S is equals to 0, then so this down NOR gate, if you see the S is equals to 0, the next input would be 0 because Q is 0. So Q is passing to the next input, means the next input for the S is equals to 0 NOR gate, that NOR gate. So for these two inputs is 0 0. So output would be 1, Q bar would be 1. So final output would be Q is equals to 0 and Q bar would be 1. So if you see in the truth table also that Q is equals to 0, hence verified. In the next one, the set is 1 and reset is 0, means S is 1, R is 0. The output Q is equals to 1, you can see in the truth table. So as S is dominating, S is 1, the output would be 1. So we can see from the truth table it is clarified. So remove the truth table. If you don't know the truth table also, we can simply verify from the circuit diagram also. So if S is equals to 1, so any one of the input is 1, we are going to have whole output as 0. Now only we saw from the NOR gate truth table. So as S is equals to 1, we are going to start our implementation from there. So as S is equals to 1, the Q bar would be 0 because the output would be 0. As Q bar is equals to 1, Q is equals to 1 because it's exactly opposite of Q bar. So you can also verify from that. How? Because as Q bar is equals to 0, so Q bar is passing to the first NOR gate. So as R is equals to 0, as Q bar is 0, so 0 0 gives our Q is equals to 1. You can verify from the truth table also. From the circuit diagram also we can verify that. The next very important thing is here is when S is equals to 0 and R is equals to 0. When set and reset both are zeros, then what we need to consider? From that we cannot calculate with the help of the truth table. We need just the circuit diagram for this. So if you consider in the circuit diagram, we need to pass S and R as 0. So after passing that, we need to assume that Q is 0, Q bar is 1. So we can take vice versa also. We will prove with the vice versa next. First, let's see with this example. So if you see Q is equals to 0 and Q bar is equals to 1, so you are going to trace back. So so already we have the feedback here. So Q will be going to the next NOR gate and Q bar will be going to the first NOR gate. So the first NOR gate is 0 1. So one of the input is 1. So for whole output Q is equals to 0. In the down also you have second NOR gate. The two inputs are zeros. So the whole output would be 1. Or we can simply say first Q is equals to 0 and Q bar would be 1. That also verified. So since the present state is 0 and 1, the next state is also 0 and 1. So already we have took the present state, that is 0 1 and 1. So Q next state, that is NS means next state, PS means present state. So you can also observe there I have highlighted in the green color, it has been changed to the next state. So the next state output is 0 1. So the same output again we are getting. So this condition is known as hold condition, because previous input is equals to the next state, means next state output. So we can say that is a hold condition. I have represented in the truth table also. I have said before only, if Q is equals to 0 and Q bar is equals to 1 is just one of the assumption. So the reverse assumption is also possible. So take that Q bar means equals to 0, Q is equals to 1, and again give feedbacks to that. So if you observe in the first R is equals to 0 and again that feedback is 0, both are 0. Both are 0 means output Q is equals to 1. So if you see the next one of the input is 1. So again whole output would be 0, Q bar is equals to 0. So you can also observe that the present state is Q is equals to 1, Q bar is equals to 0. The next state is also the same, the Q is equals to 1, Q bar is equals to 0. So this is also known as hold. The present state is equals to next state. You can also observe in the truth table. So hence vice versa is also possible. Finally, the main thing is here. If you observe why 1 1 condition, when set and reset is 1 1, then why output is the forbidden. If you observe clearly, I have passed directly over there. Then if you see the first NOR gate, one of the input is 1, then whole output would be 0. That is the condition of according to the NOR gate truth table. So the next NOR gate also, when S is equals to 1, so when one of the input is 1, whole output would be 0. Now you only say how Q and Q bar would be the same output. So this is not possible. If Q is equals to 0 means Q bar should be definitely 1, because that's the complement form. So this cannot be happen. So that is the reason this state is known as forbidden state. So remember this truth table very much carefully, that both of the inputs are 1, that is forbidden. Both of the inputs are 0, that is hold. So when reset is dominating, that is output would be 0 resetted. When set is dominated, the whole output would be setted, that is 1. So it's difficult to represent always in this circuit diagram format. So it is very simple to represent the whole block as a block. So inside that block we have some logic that is the same logic that as circuit diagram. So truth table would be same circuit diagram. If you expand the block diagram, the circuit diagram would be that same. So for the simplicity we are going to represent in this format. So as block consists of 2 inputs and 2 outputs. So inputs are SR, outputs are Q bar. So up to now what we have discussed, the truth table and the circuit diagram of the latch is just called the transparent SR latch. So transparent means we have already discussed in the previous basic video. That means it is a simple asynchronous sequential memory element. Means it will just immediately responds to the input level changes. So if immediately responds to the input levels, just we are going to have the outputs very much instantly. We don't want that. We want in a fashion, in a quiet manner, in a simple manner, in a delayed manner, so that we can able to manipulate our inputs to the outputs. So that is the required condition. So with the help of transparent latch, we cannot able to make that. So we have another kind of SR latch that is known as gated SR latch. So let's also see that. So as gated SR latch is also known as the synchronous sequential memory because it will not respond quickly to the input. It will respond as discrete time intervals because in this we have additionally called enable line. All the circuit would be same but we have enable line that makes a whole changes. So simply we can convert normal transparent latch to the gated SR latch with the help of this kind of format. So we have just combinedly, so again extra we have only one line called enable. So we can join with the normal transparent latch that enable with the help of 2 AND gates. So you can cascade like that to get the gated SR latch. So already we have saw what is inside the block of the SR latch, means the transparent latch. Simply replace the transparent latch with the already we have shown. So if after replacement, this is the circuit diagram that we are going to formulate because that just we have added to not means what we call as AND gates with the enable line. So total we have 3 inputs here, R, S and E. So in this also we are going to observe very clearly that the truth table is also very much similar because when enable is 0, whole output would be hold and whatever may be the SR, output would be hold. Means the previous state would be retained. Remaining all the things would be the same. When enable is 1, remaining all the things would be same. Because if you observe clearly, enable is 1 always. So R into 1, that is R itself. Again S into E. E means what 1? S into E means S only. So simply I have represented with E. So I simply you can see over there. As I already said in the normal transparent SR latch, so the same point will also be applicable here. Because if you consider, if you want to pass the top as S and bottom as R, so that is valid, but you are going to get output as Q bar and Q. That is very important point that you need to note as point. So the down represented that we are going to use in this video because that's the standard one, that is wherever you are go or you if you follow the textbooks also, the second represented would be shown majorly. But first representation is also correct. The second representation says that when you pass R and S as bottom, you are going to get the outputs as Q and Q bar bottom. Again the same things will be repeated. If you observe, if you want to pass R is equals to 0, S is equals to 0, that is for the first condition. Again you are going to get the same conditions. So already we have signed the transparent latch. Just we have added the transparent latch with the help of the 2 joint AND gates with the enable line. Enable is always 1. That doesn't make any sense. So always the transparent latch output would be the gated SR latch output. So if you consider that if you pass 0 0, you are going to have suppose present state as 0 1 is a present state as 0 and Q bar is equals to 1. So the same thing you are going to have in the next state also, that is Q is equals to 0 and Q bar is equals to 1. So the implementation we have already done. So suppose if you pass S is equals to 1 and R is equals to 0, as in this case S is dominating, S is 1 means set is dominating, the whole output Q is equals to 1 in this case. So because the whole conditions would be same, so I am going faster in these cases for the gated SR latch. Yeah, I hope you can do the remaining last thing, that is for 1 state as it is a forbidden state. But before that we are going to have the timing diagram analysis so that we can understand or we can relate how the output is producing. So if you consider how to draw the circuit means timing diagram analysis, that we are going to learn in this video. First let's learn that we are going to pass the clock signal in the enable line in the gated SR latch. So if you observe the gated SR latch normal clock signal I am passing in the enable line. And also, as this is the SR latch, gated SR latch, we have another two inputs, that is S and R. And finally, we are going to produce the output, that is Q. I hope you are understanding that first we took the clock pulse, that is sending into the enable line. And next we are going to have the input lines, that is S and R. So as I drawn the dotted lines corresponding to the each level. So if you observe the clock, I drawn the dotted lines according to the clock, because the clock is main here. According to the clock only we are going to produce the output. For comparing S and R, we are going to produce the output Q. So S and R are some random inputs. So I took some random clock pulses S and R. So but clock is very important here. So if you see clock, the higher level, that it represents the level trigger. I hope you know what is meant by level triggering. So for only level high, it will respond it. So let's see how to do that. The output expression, how to get the output clock pulse. So now we are going to construct the output Q. So for the output Q, it is very better to write down like that. Above that given input line S and R, up you can write. That is, if up is there, means whether it is up level, you are going to write as 1. Whether it is low level, you are going to represent with that 0. I hope you can represent all that like that. So for the representation of output Q, we need to have the truth table with the help of the enable line. So enable means here clock. So when the clock is high, we are going to compare the S and R, we are going to draw the output Q. So as we are in the high level, so you can also I have represented there. We are in the high level. So we can proceed or we can compare S and R and we can produce the output. So if you see in the truth table, S is equals to 1 and R is equals to 0. So when S is equals to 1, means set is dominating. So we have to set the output, means Q is equals to 1 here in the first case. So the next step, if you observe, the clock pulse is high only. So in that we are again going to follow the S and R. So if you see here, the reset is dominating, R is dominating, that is 1. So in this case, the output would be going down. So the next case, if you observe here, that whole level is changing, the clock level is 0. So as clock level is 0, we should not consider whatever may be the S and R. Just simply follow the previous output. The previous output is what? Here, that is 0, the low level. So just follow the previous output Q and draw the remaining whole in the low level. The next step is, if you see, consider clock is again went to high level. So in the high level, again we are going to proceed with our comparisons between S and R. If you see, S set is 1. So set is dominating. So for that purpose, we are going to set our Q to high, because we are going to compare S and R and we need to produce our output. So after comparing, set is high. So produce the Q as high, and clock level is also high. So we are going to proceed with that. So if you see, in between only we have reset as 1, high. Means reset is high means what? We are going to again 0, because reset is dominating. Or you can also see that S is equals to 0 and R is equals to 1 in the truth table. You can see that is 0. So again for the output Q, we need to go down. Again we are entering the low level of the clock signal. In this case, again we are going to follow the previous output. That is what? That is low only. If the previous output is 1, we are going to follow the high signal only. But in this case, we are having the previous output as 0. So just follow that 0 signal only when we are entering the low signal of clock. So again, if you observe, the set is 1 and reset is 0. So set is dominating. So again bring high. And finally, if you observe, the set is 0 and reset is 1. So again bring back the reset to 0. So if you consider this is the whole circuit diagram or the timing transition diagram of the Q, output Q. So you can just formulate the remaining circuit, the remaining clock pulse also. We can also simply formulate the Q bar also, just the opposite of the Q. That becomes our Q bar. That is also one of the output. I hope you understood this video, the implementation of latches with the help of the NOR gate. In the upcoming video, we are going to see the implementation of latches with the help of the NAND gate. So that is also very important. So stay tuned. Thanks for watching up to now.